Hello students, welcome to Electric Circuit Analysis lecture series. This is the first lecture in this series. In this video, we will have a look into some of the basic terminologies of electric circuits and some basic laws that will be helpful in solving circuits. So these are the contents that we are going to have a look at in this video. First, let us have a look into the basic elements of electric circuits. The basic elements of electric circuits are resistors, inductors, capacitors, and energy sources. When I say energy sources, there are two kinds. One is voltage source, another one is current source. So this is a symbol for DC voltage source and this is a symbol for DC current source. Likewise, this is a symbol for AC voltage source and this is a symbol for AC current source. These are sources of energy. So these elements are called as active elements, whereas elements which are going to dissipate the energy, those elements are called as passive elements. So best example for passive elements will be resistors, inductors and capacitors. So these elements will dissipate energy, so that's why it is called as passive elements. And elements which are going to act as sources of energy, those elements are called as active elements. So the relationship between a voltage and a current for resistor is given by Ohm's law. V is equal to I R. For inductor, the relationship between a voltage and current is given by V is equal to L into di by dt. For capacitor, it is V is equal to 1 by C integral of I dt. If the relationship between input variable and output variable for any component is going to be linear, then those elements are called as linear elements. To say if the relationship between voltage and current in case of a resistor, it is going to be form a linear relationship, so these elements are called as linear components. If the relationship between input variable and output variable for a particular component is not going to follow a linear relationship, then those elements are called as non-linear elements. Best example for non-linear elements will be diodes and transistors. An example for linear elements will be resistor, inductor and capacitor. Coming to the definition of nodes and branches. Node is a juncture where two or more elements meet together. So let me mark the nodes in this circuit. So here at this juncture, two elements VA and R1 meet together, so it is called as a node. Here three elements R1, R2, R3 meet at a juncture, so it is also a node, but it is called as a principal node because more than two elements if join at a point, then it is called as a principal node. So here this is also a principal node where R3, R5 and R4 meet, and this is a node where R5 and VA meet, and this is a juncture where VA, R2, R4 and VB all meet together. So this node is also called as ground node. So in this circuit there are totally 5 nodes. So coming to branches, branches are nothing but segments which lie between two nodes. So here between the node 1 and 2 you have a segment R1. Between node 2 and 3 you have R3. This is also a branch. And between node 3 and node 4 you have a branch R5. If this is taken as node 5, then you have VB between node 4 and node 5 and R4 between 3 and 5, branch R2 between 2 and 5 and VA between node 1 and 5. So there are totally 7 branches here. One is VA, R1, R2, R3, R4, R5 and VB. The element VB is lying between the node 4 and 5, that is also a branch, so there are totally 7 branches. Coming to the definition of a loop, any closed path in the circuit can be called as a loop. So let me tell one loop here. I will start from this node. So this is a closed path, isn't it? Coming from R1, R3, going through R4 and again going through VA and closing at this point. This is a closed path, so I can call this as a loop. So any closed path can be called as a loop, whereas mesh is also a closed path, but it will not contain any other loop within it. For example, this loop that I have drawn here cannot be called as a mesh because it has two smaller loops within it. Like this is a small loop, okay, VA, R1, R2, this is a small loop, and there is another small loop R3, R4 and R2. So this bigger loop cannot be called as a mesh because it contains smaller loops within it. So mesh is a loop where it will not contain any other loop within it. So let us identify how many number of meshes are there in this circuit. The first mesh will be this one, first mesh, which contains VA, R1 and R2. This particular closed loop does not contain any other loop within it. So this is a mesh, and this is also a mesh which is comprising of R3, R4 and R2, mesh 2, and there is another mesh R5, VB and containing R4. So there are 3 meshes in this particular circuit. There is an expression to find out how many number of meshes are there in a circuit, that is given by B minus N plus 1. So this formula gives how many number of meshes are there in a circuit. See here it is 7 minus 5 plus 1. So it is totally 3 meshes. So we have seen here totally 3 meshes. Okay. So in this circuit we have 3 meshes. Coming to Kirchhoff's voltage law, it states that in any closed path, sum of all voltages is equal to 0. So to demonstrate this, I have taken this simple circuit consisting of 2 DC sources VA, VB and 3 resistors R1, R2 and R3. So I have also marked the nodes here 1, 2, 3, 4 and 5. So the first step that you do to write the loop equation using Kirchhoff's voltage law is assume an arbitrary loop current and its direction. So I have assumed a loop current of I in the clockwise direction. So because of this current, you will have potential drop across R1, which is given by V1. V1 is equal to I into R1. And there will be a potential drop across R2, which is given by V2, that is equal to I into R2. Similarly, the drop across R3 is given by V3, which is equal to I into R3. You can mark the polarities of these potentials by taking incoming current or the terminal where the incoming current is there, that as positive, and current leaving terminal can be marked as negative. Similarly, here also current entering terminal can be marked as positive and current leaving terminal can be marked as negative. So likewise for this also. So now in this loop you have 5 potentials VA, V1, V2, VB, V3. Sum of all these potentials should be equal to 0. According to KVL, sum of all the potentials in a closed loop should be equal to 0. The second thing that you do is start from any node of your choice. Make a walkthrough through the entire loop and come back to the same node. So now I am going to walk from node 1 and I'm going to walk through 2, 3, 4, 5, and then I'm going to come back to the node 1. So you can make a walkthrough to the entire loop in any of the directions that you like. But when you walk through, you are going to meet the potential V1. If the positive polarity of the V1 is met first, then the sign given to V1 will be positive. Now for V2 also, I meet the positive polarity first, so it is plus V2. When I cross this, I meet negative polarity first, so it is given minus sign, so minus VB. Here it is again plus V3, and when I go through VA, I encounter negative polarity first, so I give minus to VA, so minus VA. So sum of all potentials is equal to 0. So the other way of writing the same equation is I into R1 plus I into R2 minus VB plus I into R3 minus VA is equal to 0. So this is the loop equation for this particular loop by applying Kirchhoff's voltage law. Students can use an alternate way of writing the same equation, that is by using sum of voltage drops. This is the other way of telling Kirchhoff's voltage law, that is sum of voltage drops in a closed loop is equal to sum of voltage rises. Okay, so to do this, we should identify among the 5 potentials which are all coming under drop and which are all coming under rise. So when you walk from a positive to negative, you consider that potential as a drop, and you walk through that particular element. When you cross minus to plus, then you can consider that as a rise. So here it is plus to minus drop, plus to minus drop, minus to plus rise, plus to minus drop, again here minus to plus, so rise. So all the potentials coming under drop are V1, V2, V3. Potentials coming under rises are VA and VB. So sum of all potential rises is equal to sum of all potential drops. So this is the other way that students can write the loop equation. Both are one and the same. This equation as well as this equation are one and the same. Coming to Kirchhoff's current law, it states that at any juncture, sum of all currents is equal to 0. Sum of all currents is equal to 0. So let me take a junction like this where there are 5 currents I1, I2, I3, I4, I5. So sum of all these currents in this junction is equal to 0. So these two I1 and I2 currents are incoming to that particular node. So positive sign is given to these two currents. Leaving currents are given negative sign. So it is like this: I1 plus I2. Leaving currents I3, I4, I5 are given negative polarity. So sum of all currents is equal to 0. So the other way of writing the same equation is sum of incoming currents is equal to sum of outgoing currents. Sum of outgoing currents. So here incoming currents are I1 and I2. Outgoing currents are I3, I4 and I5. So sum of outgoing currents is equal to sum of incoming currents. Both ways, both the equations are one and the same. So students, we have seen how to apply Kirchhoff's voltage law for a closed loop and Kirchhoff's current law for a node. In the next video, we will be looking into mesh analysis and nodal analysis.